Scientific notation is something that you've probably already talked about in your other science classes, but just to go over it, just to make sure we're all approaching it the same way. In order to put numbers into scientific notation, we're going to place the decimal after the first non-zero number, which is any number that is not a zero. We're then going to rewrite the number and multiply it by 10x. We're going to then count the number of spaces you move the decimal. This is your x, and then if the original number was less than 1, the exponent is going to be negative. So let's take a look at an example here. So in this first number here, the first non-zero number is going to be the 6. So we're going to write 6, decimal point, and then the remaining numbers, the 1 and the 5. So we're going to then write times 10, and then we have to count how many places we move the decimal. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's going to be to the negative 13th because it is smaller than 1. And then the last step here is to include the units. So we're going to include grams because grams is associated with our value. For the next number, we're going to follow the same process. So the first number here that is not a 0 is the 9. So we're going to do 9.8. Now, for big numbers like this, when you have all these zeros, you don't write the zeros like this. In the next couple of videos, we're going to talk about significant figures. These zeros are not considered significant. We'll talk about that more later. But for right now, just don't include those zeros. Just include numbers for now. So 9.8 and then times 10. And we then have to count how many places we move the decimal again. So we moved, even though there is no decimal here, it would be right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be 9.8 times 10 to the 10th. It is positive here because the number is bigger than 1, and then our unit here is meters. Why don't you try the next two on your own? Pause the video. So you should end up with 1.04 times 10 to the negative 4th seconds and 4.07302 times 10 to the 14th. PA, which stands for pascals, which is one of the units we'll be using in our gas laws unit. So the next value here we have is a number already written in scientific notation, and sometimes you need to put it back into standard notation. So what we would do is we're going to write the number without the decimal point, and then count whichever direction we need to. So this is negative 7, so we're going to count where the decimal would be to the left. So 1, 2, 3, 4, 5, 6, 7. So that's where my decimal point will be, and include any zeros that are needed there. And then this is still kilometers. The next value, we do the same thing. We have 1, 8, 9, and we're going to move the decimal to the right now. 1, 2, 3, 4. So we'll have 18,900 liters. It is good practice to rewrite your value once you're done writing it, just to make it a little bit neater. And then why don't you try the next one on your own. So in the last example, it is a negative value, so the decimal point moves to the left. So you end up with 0.00074 grams. So the next thing we're going to talk about are standard units, or the SI unit system. This is the metric system that we use in all sciences. Some of these you may not have seen before. So temperature, for example, is Kelvin, which uses the symbol K. Decimeter cubed is actually for volume. Seconds for time, that's what we're used to. PA stands for Pascal, which is a unit of pressure. It's just a good idea to know these so that when you're using certain measurements, you know that you're using the correct metric system unit. So there's a couple of values or conversions you need to be able to do. So for temperature, you have to be able to go between degrees Celsius and Kelvin. So if you take degrees Celsius and you add 273.15, that will give you Kelvin. And then density is mass over volume. So there's a couple of equal units of volume that we need to be aware of. So 1 milliliter is equal to 1 centimeter cubed, which is equal to 1 cc. So in medical professionals, they tend to end up saying cc, which stands for cubic centimeter, and we always will be using milliliters or centimeters cubed for the most part. The other one to note is that 1 decimeter cubed is equal to 1 liter. So these were intentional when they came up with the metric system to make sure that these things kind of matched out to make calculations a little bit easier for us. So next we're going to talk a little bit about percent error and the terms accuracy, precision, and what error is. So accuracy is the closeness of a measurement to the true value of what is being measured. So accuracy can be determined by one measurement, and it depends on the quality of the measuring device. So if you have a high quality measuring device, you're going to be able to have a higher accuracy than a lower quality or a cheaper device. Precision describes the closeness or the reproducibility of a set of measurements taken under the same conditions. Precision is determined by more than one measurement, and it depends on the skill. So if you're thinking of a dartboard, so with a dartboard, if you're precise but not accurate, your darts are all hitting the same area, but they're not hitting the intended target. Our goal is to be precise and accurate with all of our measurements. We want to be kind of hitting the target, and it's reproducible. So the points are all very close together. The worst combination here would be precise, not precise, or accurate, and the points are kind of all over the place. And we have ways that we can determine this, which we'll talk about a bit more later. So something just to keep in mind. So whenever we're taking a measurement, there's going to be the accepted value, and this is a quantity used by general agreement of the scientific community. So this is kind of a theoretical value, which is another way to describe this. Experimental or actual value is a value measured during an experiment. So this is the value that someone physically measured in an experiment. Sometimes there's calculations that you can do to figure out your accepted value. But also sometimes you need to do calculations for your experimental. It all just depends on the experiment. But error we define as the difference between the accepted and the experimental. So error is going to equal experimental minus accepted. So we have this formula that we use to describe it, and we multiply it by 100 to make sure that we're looking at it in terms of a percentage. But let's take a look at this example. So in an experiment, a student measured a volume of a gas to be 45.26 milliliters. The student then calculated the volume was to be 48.90 milliliters. What is the percent error? So the first thing we have to do is we have to figure out what is the experimental value and what is the accepted value. So notice the word here, that a student measured the volume of a gas. So they measured it in an experiment. So this would be your experimental value, while the 48.90 would be your accepted. So the experimental is usually the easier one to identify. So what you're going to do, you're going to plug in the experimental of 45.26 milliliters minus 48.90, absolute value of that, divided by the accepted, which is 48.90 times 100. So you're going to end up with 3.64 divided by 48.90 times 100, which will give you 7.44%. So that would be your percent error. Notice there's no sign with it because there is that absolute value.